Hello students, in the previous session we looked into many examples which were based on solving the equations of a circle. Now let us look into a theorem which gives us the general equation of a circle. Here the theorem says, prove that the equation x square plus y square plus 2gx plus 2fy plus c is equal to 0 always represents a circle whose center is minus g comma minus f and radius is given by square root of g square plus f square minus c. Let us look into the proof of this theorem. The given equation is x square plus y square plus 2gx plus 2fy plus c is equal to 0, which can be expressed as x square plus 2gx plus g square plus y square plus 2fx plus f square is equal to g square plus f square minus c, which can be written as x plus g whole square plus y plus f whole square is equal to square root of g square plus f square minus c whole square, which again can be expressed as x minus d whole square plus y minus f whole square is equal to square root of g square plus f square minus c whole square. This is of the form x minus h whole square plus y minus k whole square is equal to a square, which represents a circle having center at h comma k and radius equal to a. Hence, the given equation 1 represents a circle whose center is minus g comma minus f, that is minus 1 upon 2 coefficient of x comma minus 1 upon 2 coefficient of y, and radius is equal to square root of g square plus f square minus c, that is equal to under root of 1 upon 2 coefficient of x whole square plus 1 upon 2 coefficient of y whole square minus constant term. We note here that the equation x square plus y square plus 2gx plus 2fy plus c is equal to 0 represents a circle of radius square root g square plus f square minus c. If g square plus f square minus c is greater than 0, then the radius of the circle is real and hence the circle is also real. If g square plus f square minus c is equal to 0, then the radius of the circle is 0. Such a circle is known as point circle. If g square plus f square minus c is less than 0, then the radius square root of g square plus f square minus c of the circle is imaginary, but the center is real. Such a circle is called an imaginary circle, as it is not possible to draw such a circle. We have another point to note here. Special features of the general equation x square plus y square plus 2gx plus 2fy plus c is equal to 0 of the circle are: it is quadratic in both x and y, coefficient of x square is equal to coefficient of y square, and there is no term containing x y, that is the coefficient of x y is 0. It also contains 3 arbitrary constants like g, f and c. Yet another point to discuss here is the equation a x square plus a y square plus 2gx plus 2fy plus c is equal to 0 and a not equal to 0 also represents a circle. This equation can also be written as x square plus a y square plus 2g upon a into x plus 2f upon a into y plus c upon a is equal to 0. The coordinates of the center of the circle are minus g upon a and minus f upon a, and radius is equal to square root of g upon a whole square plus f upon a whole square minus c upon a. While solving problems it is advisable to keep the coefficient of x square and y square as unity. We have another point to note here. On comparing the general equation x square plus y square plus 2gx plus 2fy plus c is equal to 0 of a circle with the general equation of second degree ax square plus 2hxy plus by square plus 2gx plus 2fy plus c is equal to 0, we find that it represents a circle if a is equal to b, that is, coefficient of x square is equal to coefficient of y square and h is equal to 0, that is, coefficient of x y is equal to 0. Now, let us look up into type 1 equations on finding the center and radius of a circle when its equation is given. We have an important result here to solve the problems. The coordinates of the center of the circle x square plus y square plus 2gx plus 2fy plus c is equal to 0 are minus 1 upon 2 coefficient of x, comma, minus 1 upon 2 coefficient of y and radius is equal to square root of 1 upon 2 coefficient of x whole square plus 1 upon 2 coefficient of y whole square minus constant term. Now, let us take up an example. Find the center and radius of the circle x square plus y square minus 6x plus 4y minus 12 is equal to 0. Look up into the solution. The coordinates of the center of the circle x square plus y square minus 6x plus 4y minus 12 is equal to 0 are minus 1 upon 2 coefficient of x, comma, minus 1 upon 2 coefficient of y, that is minus 1 upon 2 into 6, comma, minus 1 upon 2 into 4, that is equal to 3 comma minus 2, and radius is obtained as square root of minus 6 upon 2 whole square plus 4 upon 2 whole square minus of minus 12, that gives us radius equal to 5. Now, let us solve another example of type 2 on finding the equation of a circle satisfying some given conditions, like find the equation of the circle whose center is at the point 4 comma 5 and which passes through the center of the circle x square plus y square minus 6x plus 4y minus 12 is equal to 0. For the solution, we have here the coordinates of the center of the circle x square plus y square minus 6x plus 4y minus 12 is equal to 0 are C1 3 comma minus 2. Therefore, the required circle passes through the point C1, that is 3 comma minus 2, and has its center at the point C, that is 4 comma 5. So, its radius is equal to C1 is equal to square root of 4 minus 3 whole square plus 5 plus 2 whole square, that is equal to square root of 50. Hence, the equation of the required circle is x minus 4 whole square plus y minus 5 whole square, that is equal to square root of 50 whole square, or x square plus y square minus 8x minus 10y minus 9 is equal to 0. Let us look up into examples of type 3 which involve the finding of the equation of a circle passing through 3 given points. We have an example here. Find the equation of the circle that passes through the points 1 comma 0, minus 1 comma 0 and 0 comma 1. For the solution, let the required circle be x square plus y square plus 2gx plus 2fy plus c is equal to 0 be the equation 1. It passes through points 1 comma 0, minus 1 comma 0 and 0 comma 1. Therefore, on substituting the coordinates of the 3 points successively in equation 1, we get 1 plus 2g plus c is equal to 0 as second equation, 1 minus 2g plus c is equal to 0 as third equation, 1 plus 2f plus c is equal to 0 as fourth equation. On subtracting third equation from second, we get 4g is equal to 0, which implies g is equal to 0. Putting g is equal to 0 in second equation, we obtain c is equal to negative 1. Now, putting c is equal to minus 1 in fourth equation, we get f is equal to 0. Substituting the values of g, f and c in equation 1, we obtain the equation of the required circle as x square plus y square is equal to 1. Now, we have type 4 problems which are based on concyclic points. We have an example here. Show that the points 9, 1, 7, 9, minus 2, 12 and 6, 10 are concyclic. For the solution, let the equation of the circle passing through the points 9, 1, 7, 9, minus 2, 12 and 6, 10 be x square plus y square plus 2gx plus 2fy plus c is equal to 0 be equation number 1. Then we have 82 plus 18g plus 2f plus c is equal to 0 as second equation, and 130 plus 14g plus 18f plus c is equal to 0 as equation number 3, and 148 minus 4g plus 24f plus c is equal to 0 as equation number 4. On subtracting second equation from third equation, we get 48 minus 4g plus 16f is equal to 0 and 12 minus g plus 4f is equal to 0. On simplification, we get equation number 5. Now, subtracting third equation from fourth, we obtain 18 minus 18g plus 6f is equal to 0. We can see here 6 is a common factor and it can be reduced to 3 minus 3g plus f is equal to 0. This is our equation number 6. Solving equation 5 and 6 as simultaneous linear equations in g and f, we get f is equal to negative 3 and g is equal to 0. Putting f is equal to minus 3 and g is equal to 0 in second equation, we get the value of c as minus 76. On substituting the values of g, f and c in first equation, we get x square plus y square minus 6y minus 76 is equal to 0 as the equation of the circle passing through 9, 1, 7, 9 and minus 2, 12. Clearly, point 6, 10 satisfies this equation. Hence, the given points are concyclic. Now, we have type 5 problems on finding the equation of a circle satisfying 3 given conditions. We have a beautiful example here. Find the equation of the circle with the points 1, minus 2 and 4, minus 3 has its center on the line 3x is equal to 7. Now, let us look into the solution of this example. Let the equation of the required circle be x square plus y square plus 2gx plus 2fy plus c is equal to 0 be our equation number 1. It passes through the points 1, minus 2 and 4, minus 3. Therefore, 5 plus 2g minus 4f plus c is equal to 0 becomes our second equation, and 25 plus 8g minus 6f plus c is equal to 0 is our third equation. The center minus g, minus f of first equation lies on 3x plus 4y is equal to 7. Therefore, minus 3g minus 4f is equal to 7 is our fourth equation. On subtracting second equation from third, we obtain 20 plus 6g minus 2f is equal to 0. As we can see here, 2 is a common factor, it can be reduced to 10 plus 3g minus f is equal to 0, that is equation number 5. On solving equation 4 and 5 as simultaneous equations, we get g is equal to minus 47 upon 15 and f is equal to 3 upon 5. On substituting these values of g and f in second equation, we get 5 minus 94 upon 15 minus 12 upon 5 plus c is equal to 0. That gives us C is equal to 11 upon 3. On substituting the values of G, F and C in first equation, we obtain the required equation of the circle as 15 into x square plus y square minus 94c plus 18y plus 33 is equal to 0. Here we have an interesting and challenging problem for you. Find the area of an equilateral triangle inscribed in the circle x square plus y square plus 2gx plus 2fy plus c is equal to 0. We can see here a triangle inside a circle and with the center O, and it is making angle BOD is equal to 60 degrees. Let triangle ABC be an equilateral triangle inscribed in the circle x square plus y square plus 2gx plus 2fy plus c is equal to 0. Let O minus G comma minus F be the center of the circle. Then OA is equal to OB is equal to OC, that is equal to square root of G square plus F square minus C. In triangle OBD, we have sin 60 degrees is equal to BD upon OB, that is BD is equal to square root of 3 upon 2 into square root of G square plus F square minus C. As we know, BC is 2 times BD, so BC can be simplified as root 3 into square root of G square plus F square minus C. Therefore, area of triangle ABC is equal to under root 3 upon 4 into side square. Therefore, area of triangle ABC can be simplified as root 3 by 4 into 3 into G square plus F square minus C square units, that is equal to 3 under root 3 upon 4 into G square plus F square minus C square units. Now, we will discuss about the diameter form of a circle. Here we have a theorem. The equation of the circle drawn on the straight line joining the two given points x1 y1 and x2 y2 as diameter is x minus x1 into x minus x2 plus y minus y1 into y minus y2 is equal to 0. Look up into the proof of this theorem. Let A and B be the extremities of the diameter AB having coordinates x1 y1 and x2 y2 respectively. Let P x y be any point on the circle. Join point P to the points A and B. Then M1 is the slope of the line AP that can be expressed as y minus y1 upon x minus x1, and M2 is the slope of the line BP that is equal to y minus y2 upon x minus x2, and the angle subtended at the point P in the semicircle APB is a right angle. Therefore, what should be the product of the slopes? It should be -1. Therefore, M1 into M2 is equal to -1, which can be simplified as y minus y1 into y minus y2 is equal to minus x minus x1 into x minus x2. That gives us x minus x1 into x minus x2 plus y minus y1 into y minus y2 is equal to 0. This is the required equation of the circle having x1 y1 and x2 y2 as the coordinates of the endpoints of a diameter. Now, we have an important remark here. If the coordinates of the endpoints of a diameter of a circle are given, we can also find the equation of the circle by finding the coordinates of the center and radius. The center is the midpoint of the diameter and radius is half of the length of the diameter. Here, let us solve an example involving diameter form of a circle. Find the equation of the circle drawn on the intercept made by the line 2x plus 3y is equal to 6 between the coordinate axis as diameter. Look into the solution. The line 2x plus 3y is equal to 6 meets x and y axis at A, that is 3, 0 and B 0, 2 respectively. Taking AB as the diameter, the equation of the required circle is x minus 3 into x minus 0 plus y minus 0 into y minus 2 is equal to 0. This we could write with the help of the given expression for diameter, that is x minus x1 into x minus x2 plus y minus y1 into y minus y2 is equal to 0. On solving this, we get x square plus y square minus 3x minus 2y is equal to 0. So, students, hope you enjoyed studying circles under the chapter conic sections, and in the coming sessions we shall discuss about other curves, that is about parabolas, hyperbolas and ellipses. Thank you.